Hey, hello, engineering camp. I'm really happy to be here. I'm sorry you're not here with me, but we're going to do something that's a little bit different from some of the other camp sessions. I'm going to show you something, an experiment you can repeat and also eat at home. I'm going to give you a little safety talk beforehand. We're going to be working with high temperatures, and we're going to be working with a sugar solution. So that means high temperatures. You want to be careful. You want to make sure that you've got appropriate protective equipment around, like a little hot pot grabber, that you are wearing, say, an apron, so if something splashes, you don't get burned. You want to make sure that you have cleared with your parents that this is a thing to do. And you really, really want to be careful that there are no spills or ways that you can pour a hot sugar solution onto you or another person or a pet, because not only is it at high temperature, but it's very sticky. So it doesn't just like hit you and roll off, it stays there. And that can lead to a much worse burn than if you had, for example, just a little bit of boiling water splash on you. So if you try this at home, one, make sure it's okay with whoever's in charge of the kitchen at your house. Two, make sure that you are careful to avoid spills, that you have positioned everything carefully, that you are wearing an apron and shoes that cover your toes and that sort of thing. And then have fun, because we're gonna correctly and incorrectly work with sugar. And you're gonna see how things turn out both ways. And it's a really simple recipe, and so you can do this yourself later. You can memorize it. You don't even need to write it down. This is Bucknell University's food lab, and this is the one lab here where it's actually possible to eat the experiments we run. We keep it very clean, so I've just bleached out everything before coming in, and I washed my hands. My hair is back up and out of the way. I'm not cooking for anybody else today, so I don't need a hairnet. Yeah, well, wait, let's get to it. So I'm going to turn the camera around so you can see. There we go. And now I'm going to be all crazy and distorted. So we are going to work.
Professor Vigeant, I'm just going to, can I just jump in and just give one little tip here for some people?
Yes.
I know that my default Zoom setting, I have like 25 little squares on the screen. If that is the default setting for anyone else, in that case, if you're seeing that, Professor Vigeant's window is very small. There is a choice to click on speaker view. So if you click on that, that will put whoever's talking as the big window on your screen there. So if any of you are having trouble seeing Professor Vigeant in the little square, if you click on speaker view, that should bring her up to the big screen size for you, so you can see this experiment appropriately.
Yeah, thanks a lot, Todd, because you definitely want to see what's happening in the pot. Now, what's happening in the pot right now is nothing because it's empty. But what we're going to do is I'm going to take half a cup of sugar. We all know what sugar is. And I'm going to put that in the pot. So I'm going to come to my first question that I want you to please type in the chat if you know this. Could somebody tell us, remind us all what it means when something dissolves in something else? So if I was going to dissolve chemical A into chemical B, like what would it mean that happened? So if you know that, please type it in, and I will ask Todd to read it out. Yep, because right now I can't see the screen at all. I'm just like waving my arms at you.
We have a couple people that have said diffusion. Still waiting on some more people to type in some answers. We have one person that says the solute is diffused completely into the solvent.
Okay, I like that. And while you're all typing, I'm going to ask the follow-up. So we have something that kind of goes completely, that's what we mean by diffused, completely into something else. So can we see it anymore? If I dissolve one chemical in another chemical, can I see it?
I think we do have a couple people that are still answering your first question. They said the molecules of the solute are separated and surrounded by the solvent.
Ooh, I like that one. That's a good one.
And then we are getting a lot of no's to your second question. So
good. Excellent. Thank you, everybody. All right. So does sugar, which is the chemical sucrose, so this is pure sucrose right here, does sugar dissolve in water?
We have a good number of yeses there. So
Okay, good. I'm glad we agree. So I just put half a cup of sugar in here. I am now going to put, this is a tablespoon. I'm going to put 2 tablespoons of water in here. All right, and we all just agreed that sugar dissolves in water. So I'm gonna just sit here and we're gonna look at it, it's gonna dissolve, right? Yeah, no, okay. Because there's this thing called the solubility limit, right? So if this sugar has got to wend its way in between all these water molecules, there's a point where there's too much sugar and not enough water, right? We could have more sugar than fits in the water. And if you look at this, you can see that is indeed the case here. We know because it's not clear, right? It's still all cloudy. You can see, you know, even if I kind of stir it up, it's still chunky even. So I'm going to stir it up really well to make sure that all of the water has contacted all of the sugar. But you'll notice it's still like this is not dissolved. What do you think I should do if I want to dissolve this sugar into this water? If it's even possible. Because I mean, it's half a cup and 2 tablespoons. That's a lot more sugar than water.
we are getting a lot of heat it up, mix it, add more water. Those are some of the answers that are coming in.
Oh, thank you. Okay, so I'm gonna not add more water. You are correct. Adding more water would work, but it won't get us the result we want. I didn't tell you what our result is. We're making lollipops. So that won't get us to lollipops. Stirring more changes how fast sugar dissolves in water, but it doesn't change how much. So if we've hit the solubility limit, which we have, stirring it just makes it homogeneous. It doesn't change it. So let's try that last option. Let's try heating it up. This, and it makes a little bit of noise. This contraption here is what's called an induction cooktop, and it's neat. It, rather than the surface itself heating up, it uses electromagnetism to make the pot heat up. So this part down here stays cool, but this up here heats up. And you can hear it does it really pretty fast. Can you see there's little bitty bubbles starting to form? And I'm gonna break out, this is a no-touch thermometer. We are all gonna get really familiar with this kind of thermometer soon. So I'm gonna point it at here and try and make it so maybe you can see. The temperature is gonna hop because it's not at a uniform temperature yet, but we're seeing it's a reading in Fahrenheit. So water boils at, anybody know that number?
212.
In Fahrenheit. Very good, 212. So if I come over here and try and hit this so we can see, oops, hard to see. It's saying 212 and up to 240. Can you see something here? Something interesting has happened. See if I can get, whoops, it doesn't like that I picked it up. Can you see? Look at the spoon. We are much closer to having this dissolve. This is very close to clear. So I'm gonna stir it around. I'm gonna get this nice and well mixed. And I am, so I wanna talk about why stuff dissolved when we raised the temperature. Even though it was still just a tiny little bit of water, and in fact, we're losing water all the time. You probably can't see this, but if I can definitely feel it right here, I'm getting water on my hand in the form of steam. So we have this sugar kind of dissolved, kind of melted, in just that tiny little bit of water. And that's really what we want if we're going to make a candy, because we are gonna need what's called a supersaturated solution. So remember, at room temperature, when I tried to put that sugar into that water, it wouldn't go. now I've heated it up and it's dissolved, and that's awesome. And when I cool it back down again, we want it to kind of stay in that solution-ish, and not go back to being a whole bunch of sugar crystals. And because we've heated it up, it should do that. But there's something really weird going on here. Can you see this? There's like little chunks happening over here. Also, it's starting to turn brown, which I expect. So that means the temperature is around 350 degrees. Holy cow. Most of the water is gone. I'm going to turn this off and I'm going to pour it out. So I'm going to scooch this out of the way. And hopefully you can see. Tell me that this is showing up. They're looking here.
We are good. We can easily see, so perfect.
All right, so I'm pouring this out. So this is the part that's like dangerous, right? You don't like, it is very bad to get 300-degree sugar onto your body. So don't do that. All right, look, it was beautiful. It was clear. We're gonna let that sit for just a second, and I'm gonna take some of this and mix it around, because I want to show you something interesting that happens here. So we got this lovely color, and it's got this kind of caramel-y flavor. So those of you who watch cooking programs will recognize this as kind of like the stuff that's on top of creme brulee, for example. So I'm going to mix this around because I would like to make, whoops, taffy. And this is non-stick foil here, but I am not having success. My gosh, what is happening here? Can you see what just happened? This is still incredibly hot. If I measure its temperature, it's over 220 degrees. So that's why I'm not going to touch it. I am definitely not going to lick this spoon. I would regret it very much. But look at that. Those are like, it re-solidified into crystals, even though it's super high temperature. And if you look at what this looks like, do you see every place I touched went bam, turned into crystals? Whereas where I let it sit, it's only a little bit crystalline. We're going to let that sit more while I do the second bit. So sugar really, really, really wants to be crystals. Super duper. It wants to be crystals. It is almost impossible to make a good lollipop out of just sugar. And I'm going to show you the science behind that in a second. So what can we do if we want to mess with that? So I'm going to go back to my pot. I'm even going to just reuse it without cleaning it up because I'm still just working with sugar. I am going to make a change. Here goes half a cup of sugar into the thing. And here goes, again, 2 tablespoons of water. By the way, a really, really excellent pastry chef skips the water because you're going to boil it till the water goes away. Almost all the water goes away anyway. I'm going to add something else that is going to keep it from getting crystally. This is corn syrup. If you don't have corn syrup at home and you want to try this, you could use honey. Honey will do the same thing, and it'll also give you honey flavor. And I should have loosened this lid before I was standing here in front of all of you. Oh my gosh. Remember, I told you, it's super sticky.
It's your workout for the day.
It is. There we go. All right, I got it. I'm going to add about a tablespoon, but because this is so sticky, I'm going to just eyeball it as opposed to measuring it because I don't want to have to wash that off of the tablespoon. Okay, so here we go again. Half a cup of sugar. So what the heck is going on with corn syrup? Why do I think this is all going to be better with corn syrup? And look at what happened to the side of the pot here. Like this is pretty intense. So back up to high temperature. And let's see what's happening. Let's see what's going to happen now. So while this is heating up, I want to show you a thing. Actually, I'm going to do it this way. I am going to move over here, and I'm going to take this with me, and hopefully I will be able to get it back. All right, little bit of chemistry up here. First, sucrose is that big molecule up top. Every place there's a corner, it's a carbon, okay? Fructose, this little molecule down here. Hold that thought in your head for a second, because this is starting to boil. All right, so I'm gonna explain what the heck I was doing with that in just a second after you get back here. All right, so you see that we are boiling once again. Whoa, you see that my camera almost went for a swim in the sugar. See, this is why.
Everyone, I think we may have lost Professor Vigeant. So hopefully her phone did not fall into the boiling hot pan or anything like that. So we may just have to hold tight here for just a minute and see if she can get reconnected. So apologize for the brief interruption here.
Sorry about that. Had a little bit of a disaster. It's okay. It's okay, folks. All right. So here we go. Attempt number 2. This is half a cup of sugar, a tablespoon of corn syrup, and 2 tablespoons of water. And we're also getting some bonus sugar in here because the crystals are coming in off the wall. All right. And also, before I lost transmission, did you all get to see the sucrose and the fructose? I know they're complicated.
Yeah. Yes.
But, oh, good. Okay. So, sucrose is what's in here. That's the sucrose. You eat it all the time. Fructose is what's in here in the corn syrup. You've probably encountered that before too. And something that's really important, if a chemical is going to become a crystal, is the chemical's shape. And so I showed you those shapes, and we'll go back to those shapes in a moment after I am set, after this is not boiling. So you'll notice, again, it dissolved. And it didn't dissolve just because I put a little extra liquid in it with the corn syrup. It dissolved the same way it would before. And you can see it's turning a little brown, so it's around 350 degrees. So I'm gonna turn the heat off. Once again, I'm gonna scooch that out of the way, and I'm gonna let you see what happens over here as we pour this stuff out. Oh, that smells so nice. I am sorry you can't smell it. Now, if you are not into just eating sugar-flavored sugar or caramel-flavored sugar, that moment right there would be when you could add a little bit of flavor. So if I wanted to make this into a lemon lollipop, I could even just, actually, here, I can do it right here. I can pour it on top. And now I am going to mix it thusly. And so now I'm gonna have lemon. Well, it's not exactly gonna be a lollipop because I didn't stick a stick in it. I'm gonna separate some of this candy out, and I'm gonna try and make taffy out of it. You say, what the heck is happening with taffy? Well, here you go. All candy, you know, from Starburst to Skittles to Jolly Rancher to Lollipop, I'm gonna accept chocolate for the moment, is fundamentally a supersaturated sugar solution. That's what it is. Caramel, fudge, all of that, supersaturated sugar. And then we just build different things on top of it. So this here, it's way too hot to touch, so I am not touching it yet. But the difference pretty much between stuff that is gonna come out as lollipop-like, it's gonna be hard and crispy, and stuff that is gonna be taffy-like is air bubbles. And the way I get air bubbles in it is that once it's cooked, I've got to mix it. And if you've ever been to the beach or the fair and seen someone running a taffy machine, what they're doing is taking this kind of sugar solution with a little bit of corn syrup and mixing it. Now you remember what happened over here when I took the sugar syrup and mixed it. It went all to crystals. Well, here, I put that corn syrup in, and you notice it's gone all to sticky, but it's not getting crystals at all. And you'll see that this stuff, or I'll try and hold it close to the camera so you can really appreciate. You see, ooh, look, I've got threads. Oh, the threads are so neat. Oh, wow, check that out. These threads, if you spin them really well, that's cotton candy, just so you know. But if you look at this, you see how it's getting to be shiny? That's because it's starting to trap air bubbles. And those air bubbles, when they're small enough, start kind of looking like they're just white. And that's why a thing like Starburst, which is a taffy, is cloudy looking, because it has all these air bubbles trapped in it. And that makes it so, you know how sometimes you bite in a lollipop and it sticks in your teeth? But a taffy, well, it sticks differently. So here you go. Oh, wow, look at that. That is so beautiful. This is still, let's check its temperature. 150, 160 degrees. So barely, just sort of touchable. Ow, not really touchable. Don't touch that. But you see, this is getting quite sticky here. So something else really interesting is happening. And I'm going to hold this up because I think I can get this close to you now. So I'm going to set that there. So I want you to see there's 4 different things happening on this cooling tray. This is the pure sugar solution that has cooled down without me monkeying with it. And here is the sugar solution that cooled down with me monkeying with it. You see, it's very hard and it's very crystalline. This is the sugar corn syrup solution that cooled down. This is the without me monkeying with it. And this is the part that I was mixing. That's a huge difference, which you can see on the left and on the right. And a fun, you know, kind of bonus piece of material science here is when I was pulling on this, I can go back to pulling on it. Now it's still warm, but it's definitely touchable. So now I can do what you're supposed to do with taffy, which is pull it by hand. Oh, wow, look at that. It's lovely and shiny. What material that maybe you've seen, but not, you know, probably not worked with, but what thing have you seen that kind of oozes the way this oozes? Have you seen something like this? This is type into the chat. What's a material that you've seen people work with, maybe on TV, maybe at a fair or something like that, that kind of has this sort of melty, then stretchy behavior?
We're still waiting on some answers here in the chat. The one person mentioned hot glass. We've had another glass. So.
Well done. Glass is what I'm fishing for. And in fact, you would see this if you'd been around like people working with hot metal, you could see some of this there too, but it's at much higher temperatures. What we have done here is we have where there's no crystals up out here. This is kind of amorphous. It's a lot like glass, right? You can see right through it. It's nifty. And as it has cooled down, initially it was what we'd call plastic. It was something that, even though it's not like made out of plastic, it was something I could mush around and move and stretch and pull. But then as it cools, now what happens? Does it mush? No, it snaps, right? So in the middle there, it hit what's called the glass transition temperature, where it went from behaving kind of mushy to behaving as a thing that fractures. And if you've ever seen someone do an experiment, maybe someone did this earlier this week, where you pour liquid nitrogen on stuff, right? What you're doing there is taking things that are softer and pliable at room temperature and making them so cold that they behave like a glass. Candy will do this glass thing right now. So there we go. Look at that. Isn't that lovely? See, it's pretty. We can look through it. Anyway, so this is how things come out with a little bit of corn syrup. With corn syrup plus mixing, you get this nice color. With just sugar, Can you see? We get crystals even in the part that was kind of like a glass. The crystals, it really wants to be a crystal. So I want to show you part of why that happens. But listen, that lovely crack. And all of this is edible. I'm not popping much of it in my mouth right now because I want to continue to be able to talk, but yeah, I made a lemon lollipop. It's tasty. It's sticky. And you saw how fast that was. So let's do a little bit more of the science. Now I'll take you on a lab tour. All right, so we are walking back over here. On top, we have sucrose, that's pure sugar. On the bottom, we have fructose. Anyone notice something that these two things have in common? I know it's tricky and no one's had orgochemistry yet, but maybe you can spot it.
Just waiting to see if we have any guesses here in the chat. Someone mentioned the CH2OH in both of them.
Oh yeah.
The five-sided ring, the way it has a pentagon.
Oh, and yeah, okay. And I see someone said fructose is half of sucrose. Exactly. Yeah, so let's talk about both of these things. And I am gonna set down the camera for a second and move things around just a teeny little bit so I can show you what's going on here. All right, so things that are important that they have in common. So this thing, you know, like these bits hanging off here, yeah, those are the same. Good eye. Also, what's this stuff? Can you even see that? I'll write it twice. It's in blue. If I write H-O-H, normally that's not how it's written, but I'm writing it this way so you can see how it lines up. What is that stuff?
A lot of guesses of water.
Yes, well done. That's water. So water does this thing called hydrogen bonding, where the hydrogen that's on one water molecule is not only happy to be connected to its own oxygen, but it's kind of interested in flirting with this other oxygen over here. That's what makes water so sticky with itself. You'll notice that there's lots of things with the little OHs on it all over sugar. And that's why sugar is so soluble in water. Anyway, as you push the water out by raising the temperature, the sucrose, as I said, really wants then, instead of sticking to water, it wants to stick to other sucrose molecules. All right? So if you can imagine, this Lego brick, the size Lego brick, is our sucrose molecule. And so when you have a bunch of them and there's no water in the way, they line up really well and are perfectly happy to make really stable crystals. That's what we were seeing in the white chunky bits in the sugar solution. See? Nice stable crystals. Now, as you all were pointing out, fructose, so here's the fructose, this part here is the same as this part here. Sucrose is what's called a disaccharide. It's two sugars stuck together. One of those sugars is glucose. There's a glucose over here, and it is kind of holding hands through an oxygen with a fructose. So when we add corn syrup, we are adding, or honey, we're adding fructose to the mix. And so you remember I was representing sucrose as this kind of Lego brick, right? Then we could imagine maybe this is a glucose and this is a fructose, right? And together they're the same. Now we just added fructose and not even that much. So watch what happens if I take this apart again. So here I go, I've got all this sucrose and it wants to make a crystal as the water disappears, but I've got some fructoses floating free. And so the fructoses are like, yeah, man, get me in on this. I want to join. And then when the sucrose goes to make its crystal, it can't do it quite as well because the fructose has taken some of the spots. It disrupts the crystal lattice. And that's why it's much easier. In fact, it's really hard to get nice, pretty crystal things with sucrose and fructose mixed together. So that's why a lot of the candy that you're familiar with will have both of those things mixed together, because you can make that lovely clear lollipop stuff. Whereas working with just sucrose by itself, you have to be super duper careful not to stir it, not to allow any dust into it, or the second it gets a chance to, snap back into crystals. But either way, any way you do this, it's all kind of yummy stuff, right? That is, if you're into sugar. It's still all slightly toasted sugar that has caramelized, and people tend to like that, so that's good. All right, so that is that experiment. I can address some questions about this, or I can run a little additional piece of this experiment if you like, or we could start the lab tour and do the questions after that. What are we into?
I think at this moment, I don't know if we have any questions. If anyone does have any questions, feel free to put them in the chat, or even feel free to unmute yourself if you're bold and want to. You're more than welcome to. So maybe if you want to do one of those other options first, and then questions may start to come to people's minds here, and we'll throw them out when we get them.
Alrighty then. Let me flip the camera around, and we will do this Bucknell tour guide style tour of the food lab. So what we're trying to do in the food lab is a few things. One, basic experiments, so students here can learn more about food science and food engineering. So that is, how are foods designed so they stay shelf stable for the months that we want them to be okay on the shelf? How are foods designed to be nutritious and tasty and attractive and survive the packaging process? All of that good kind of stuff, plus food science, because you need to, if you're gonna design something to last a long time, you need to understand, for example, what sucrose is, okay? So what we have in the food lab here is we have, let's see, our food library. This is a new space, by the way, so there's still some things that are getting installed. So there's places where you'll see boxes. We have a number of tools that we like using, including an ice cream machine. We have some ingredients, and the ingredients, most of them are things that you're familiar with. Like if I turn and show you this, you'll see there's raisins and sugar and flour and whatnot. But there's a few things that are a bit more special that are in here that you would see in foods that you have eaten, but not what you've made at home. So for example, we have guar gum. Guar gum. Where have you seen guar gum before? We have no idea. Well, go next time you encounter some ice cream, please look at the label and read the ingredients carefully. There's a few things where we want to stabilize a food and keep it in its nice gelled state for longer than it might be otherwise. There's foods where we don't want crystals to form, and that helps that. We have a lot of basic normal kitchen stuff, like a stove, multiple stoves, microwave, but we have a few things that are special, and so I'm going to show you some of the special ones right now. We have what is called, okay, I don't know what that is. What is that? It's a colorimeter. It's a thing that measures colors. Why do we care about food's colors? That's a good one. Okay, so I can see the comments now. So yes, appeal is very important, right? There's plenty of things where, say, you slice an apple, pardon me, and it goes a little brown, and you're like, ew, no, but really it's fine. It's not bad for you. It's you know, it hasn't become poisonous all of a sudden. It's fine, but that's not so appealing. So we do need to track color for if stuff is appealing. We also need to track color because when a company makes a food, they want to have it look the same every single time, over and over and over again. And It's, you know, if you just go by pictures, you can doctor a picture and change its colors. So it's nice to have a really good technical measurement of its color. We also have a pH meter. Maybe you have used pH meters before. That's a pH meter. What's a pH meter do? Measures acidity. All right, cool, thank you, yeah, yes. So turns out acidity is really important in foods. Having foods be the right level of acidity, well, those of you who like Sour Patch Kids, you know that acidity can be part of something being tasty. But did you also know acidity can be part of keeping foods safe? If we want to have a food that can sit on a shelf for a long time without bacteria or mold growing in it, one of the ways we do that is we make that food into an acid. That's part of what you're doing when you make pickles. Okay, so that's all cool. And we have a whole lot of scales. And a scale sounds like it's not so exciting, but it is a really important measurement for food, because turns out what I was doing where I was like, oh yeah, we're putting in half a cup of sugar, that's very, very, very imprecise. And if we want to know exactly what's in our food all the time, going by grams and kilograms is the way to go. And it's what happens, for example, when Frito-Lay is making your corn chips, that's what they're using. And we have some other stuff. I'm going to show just two last things over here. We have this thing. I don't know if you've seen this before, but this is a fume hood. And we have a fume hood because we might be working with food that is safe yet stinky. What's an example of a food that would be okay, but like might smell up the room? How? Oh, ooh, that's a good answer. So I said cheese and like I see durian. Now durian, after we're done with this, y'all go Google durian if you don't know what it is. It is a fruit that is very tasty, actually. I've had durian candy, but because it contains high levels of sulfur, it makes a smell that is a little bit garbagey, I'm gonna just say. So when you're working with that, so we got some things about onions too. When you're working with that, it is nice to not have to breathe it. We have the hood mostly for one of these other answers that was given, for things like cheese. There's a lot of foods that are made by fermentation. And fermentation is when you have microbes that eat the food and turn it into something that is yummy and better preserved because, well, the microbes have already eaten it. And so cheese, especially say blue cheeses, are like that. Yogurt is like that. Beer and wine are like that. And all of those in their processing tend to be kind of stinky. And so that is why we needed a fume hood in here. Pretty much people have been okay with the onions so far, but we'll see. If we have a particularly onion sensitive person, we will definitely think about that. What we do in this lab, so you'll notice, you know, there were some fancy and cool and different than home things, but there's a lot of things that are similar than home, except just a lot more space. What we like to work on here, in addition to learning, is helping local, usually food-based businesses with problems they have. So for example, we have helped a local producer of apple cider and juice to come up with new flavors of juice. We have helped a ice cream company to come up with new flavors of ice cream. We worked with a chip company whose name I won't use to help figure out why their chips were going stale, why people were complaining about their chips going stale. And so we do a lot of kind of practical problem solving here. And we try also to invent new foods ourselves, or new approaches to old foods ourselves. And so, oh, I can't quite see all of that question. It says something is there.
I can read it out for you. Is there a food science or engineering major at Bucknell, or is this a class that is part of another major?
So this is a class that is open to, well, pretty much everyone with permission, but engineers automatically. It's in the chemical engineering curriculum. Bucknell doesn't have a food science and engineering major, but it does have a food systems minor. And the food systems minor is very popular. It has this class that I've just demoed built into it, and also things to help you understand the overall food system, the ways that distribution and farming and manufacturing all come together to get people the food that they need and want. We work a lot with the Bucknell Farm, which is a neat thing. So up here on the hill behind me, outside, obviously, there is a farm. And it's not huge. We're not talking 50 acres, but they are growing things and they are studying what they're growing and how they're growing it. And so that is a cool thing, a cool kind of living, learning laboratory that folks get involved with. All right. And that there is, now we are at Q&A time. So I'm happy to hang out here and answer questions for as long as anyone's got questions. And other than that, thanks a lot for coming. Again, if you're gonna make yourself some candy, some hard candy like I just showed you, it's easy, but be safe, be aware, hot materials that are sticky. So do all of that good stuff. Also, I wanna note, just so you don't irritate people in your family. So this is what the pot looks like. Now it's cooled down, I can show you. Like that, it looks kind of gunky and oh dear. If I just sit it down and put water in it, because lots of water, because sugar is soluble in water, it'll just come off all by itself. So just when whoever in your family says, hey, please wash that pot out, you say, I am washing it out, just let it sit there full of water for about 6 hours and it'll be fine.